So we're trying to come up with a protocol to have a classical verifier check the result of a quantum computation, right? So in this picture, here's a verifier. He's purely classical. So let me write that here. So it's a classical verifier. And the verifier is wondering, well, what happens if I run a quantum circuit, C, does it accept or not? The classical verifier can't do this on its own, so it's going to use the help of an untrusted prover. And in this specific situation, it's going to also have this trusted measurement device, right? So the first step is, the prover is just going to send some quantum state over to this trusted measurement device. And the prover is going to claim that this state psi is somehow a proof that this circuit would have accepted. The verifier is going to check this proof by first computing a random Hamiltonian term, hi, and hi comes from this Feynman-Kitaev variant that we discussed last time. But the way we should think about it is that really this Hamiltonian term is a specification of some basis for all of the qubits. So it's going to say measure qubit 1 in the x basis, second qubit in the z basis, and so on. And the Hamiltonian term is also going to say there's a disallowed outcome. Like this is the outcome for which we give an energy penalty. Right, so that's just going to be a sequence of outcomes B1 up to BR, if there's R qubits. So the verifier is going to send this basis, this basis setting to the trusted measurement device. It's going to measure this state psi and get all these outcomes. And the verifier is just going to reject if it gets the disallowed outcome. Otherwise, it's going to accept. And as we kind of argued last time, this is a good protocol for this quantum circuit. Like if C is a yes instance, meaning that it accepts, then with high probability, the verifier is going to accept, right? Because basically the prover is going to send the ground state of this Hamiltonian. And then the verifier will check that it is indeed a ground state. But otherwise, no matter what state the prover sends over, there is no low energy ground state. So the verifier is going to reject with high probability. Right? So that's just like a reminder. But it's kind of annoying to have to rely on this assumption that there's this trusted measurement device, right? We would like to have a verification protocol where the verifier is just completely classical. And so we're going to do this with the help of using two untrusted provers, right? So we're going to have two provers, Alice and Bob. The verifier is just by itself now. And the main idea is we're going to play a non-local game, like the magic square game, between Alice and Bob to force one of them to become actually a trusted measuring device. Right, so the moment you play this, let's say the repeated magic square game, we know that what Alice and Bob must have shared before the game started is a bunch of EPR pairs. And when we send them different questions in this game, like for example, you're sending Bob these, for each instance of the game, you're telling him to measure different cells of these 3x3 grids. Bob is going to measure specific poly measurements, right? Like the ones we just described, like ZZ or IZ or IX or whatever. And he's going to truthfully report the outcomes of those measurements. So, this rigidity guarantee is very powerful, and we're going to use it to design a verification protocol. So here's the outline of the protocol. Here's the start. So the verifier is going to flip a coin. And based on the coin, it's going to do one of two things. One is it's going to play a rigidity test. Like it can just play the repeated magic square game with Alice and Bob. Right. And if Alice and Bob succeed with high probability, we know what that entails. But with probability 1/2, the verifier is going to play an energy test with Alice and Bob. And the whole point of this energy test is that Bob is not going to know which subtest he is in. He cannot distinguish between the two. So if he wants to, so basically his behavior in these two tests are going to be exactly the same. In particular, he's going to be measuring his qubits using these poly measurements honestly. So, but one issue is that he's measuring EPR qubits. He's not measuring this ground state psi that came up in this measurement protocol. So how do we get that to work? The idea I mentioned last time is we want to have Alice teleport the supposed ground state over to Bob. So let's write that down. So we're going to tell Alice to teleport a supposed ground state psi to Bob. Right. So I'll review like what quantum teleportation is in just a second, but let's just assume that Alice is able to do this. And then we're just going to simulate the rest of this verification protocol. So we're going to pick a random term, HI, right? Which remember consists of this basis, so forth, and it has the forbidden outcome. Let's call it B1 up to BR. And we're going to embed this basis choice into magic square questions. So Bob is just going to get a bunch of magic square questions. And because of the rigidity test, we know that he's really going to perform this basis measurement as we expect him to. Right. And then well, let's call the outcomes M1 up to MR. There's going to be an intermediate step that I will describe in just a minute. This is called the teleportation correction. So all of these measurement outcomes will get post-processed into a different set. And then, but then we just do what we did before, which is except only if these post-processed outcomes are not equal to the forbidden outcomes. Okay, so this part looks very similar to the measurement protocol from before. I just have to tell you like what this teleportation process is and what this teleportation correction is like. Okay, so let's have a sidebar, which is, let's discuss what quantum teleportation is.
Wait, so all of this in blue is the energy test?
Yes.
So why does Alice need to send Bob a ground state? Can he come up with one on his own? Oh,
great question. So Bob could definitely come up with his own ground state, but the only problem is when we're playing the magic square game, or when we send him these magic square questions, the only guarantee we have is that he's measuring his half of the EPR pair.
Mm-hmm.
Like, I mean, on the side, he could have whatever other quantum state psi, but we don't have any control over what he's doing with that state.
Okay, I see.
Yeah, that's a good question. Yeah, Bob could have, zillions of copies of the ground state, but we just can't trust that he's going to measure it properly. So this is why we need the teleportation to get this to work. All right, so yeah, what's quantum teleportation? Well, it's, again, we have Alice and Bob. Let's say they share one EPR pair, and Alice has a qubit that's sitting on the very left-hand side, and it's in the state psi. So quantum teleportation is a protocol where Alice first performs an entangling measurement on these two qubits. So when she measures these two qubits, she gets two classical outcomes. So these will be 2 bits, let's call them E and D. And after she's measured, then the state of the system collapses into the following. So Bob, on Bob's side, he will have, he still has his qubit, but it's now in the state x to the e, z to the d. So x and z are these Pauli operators applied to psi. Right? So Bob basically has the qubit that Alice had, except there is this correction. There's this like spurious Pauli correction that's applied to psi. So we call this the Pauli correction. So let's label this as step 1, this is step 2. And then in step 3, Alice is going to send her 2 bits over to Bob. And then Bob can undo this Pauli correction in order to recover the quantum state psi. Right? So this is quantum teleportation, right? We call it teleportation because it seems like Alice can transmit an arbitrary qubit to Bob just by sending only classical information. But of course, they have to share entanglement beforehand. And this is an EPR pair.
The n qubit state teleportation analogous?
Yes, basically you just do this n times, 1 for each qubit.
And that'll work even for a highly entangled state.
Definitely, that's a good point. So first let me say we call these the teleportation keys. These, right? So because we think of as keys as unlocking the state on Bob's side. And Sumner asks, what about teleporting n qubits? We just do this for each qubit. So the point is that even if this qubit psi was entangled with some other qubit here, after it's teleported to Bob, it still maintains its entanglement with that separate qubit. Okay, so another way to put it is TP doesn't break entanglement. Okay, so here's the thing. When we tell Alice to teleport a supposed ground state psi to Bob, let's say that she does what she's told, then she's going to get all of these corrections. So or yeah, these teleportation keys. All right. So imagine that she really did do the teleportation. Then after this step on Bob's side, let's see. Oops. Right, so what used to be EPR qubits on Bob's side have now collapsed into the desired state, except it has this poly correction. Right? And we don't want to tell Bob that we're doing anything different from the magic square game. So we can't give him the teleportation keys to undo, because otherwise he'd know what's up, right? So instead, we're going to have to do something different. We're going to have to do the teleportation corrections ourselves, like we as the verifier. The point is, so this is what he gets on this side. And then after it's collapsed to this, Bob gets, the magic square questions, y1 up to yr, which tell him how to measure. So he measures this, slightly messed up quantum state using the basis measurement. But the good thing is that even though the state is messed up, we can predict what the measurement, or we can correct the measurement outcomes in a predictable way, provided we know what the teleportation keys are. So and I'm going to tell you how this correction happens. So MI prime, right? This is going to be like the adjusted measurement outcome. It's just going to be MI if the ith basis was just the identity. I mean, the reason we do that is because we don't, if the ith basis is identity, we don't actually care what the measurement outcome is. If the ith basis measurement is x, then we're going to actually flip mi depending on what di is. And if the ith basis is z, then we flip it depending on what ei is. Okay, so what's the reasoning here? Like, it's not too hard to check, but basically suppose that di was equal to 1, right? So so we actually have a z correction here. But we're measuring in the x basis, and the point is that this z, the z correction will flip between the two outcomes of your, it'll basically apply a bit flip to your the result of your x measurement. And then the opposite thing for when the ith basis is z. Okay, so hopefully that makes sense. Like, the gist is you just have to make a correction based on what the teleportation keys are. And this correction can be done completely on the verifier side.
Why do we trust that Alice has given us the correct keys?
Great question. So we don't trust that she's done that. Yeah, let me get to that in just a second. So we're still assuming that Alice has done the teleportation correctly. If she's done the teleportation correctly, then the point is these MI primes will be as if Bob measured the proper state psi in the right basis. Right? And that's exactly what we wanted because that's what the trusted measurement device did for us. Okay, good. So what about the case when Alice doesn't do this honestly? Well, we only consider this case when we're in the no case, right? So right, so meaning that this Hamiltonian doesn't actually have a low energy state. So there is no state psi that Alice could send over that would, measure to have low energy. So she's going to do whatever she wants to do. But the point is, it doesn't really matter because she's going to maybe generate some arbitrary sequence of teleportation keys E1, D1 up to ER, DR. And Bob is still going to do the measurement honestly, right? Because we forced him to. And no matter what the teleportation keys are, there's nothing that they can be set to that would force the measurement results to look like they had a low energy state. So let me write that. All right, so I wrote a long sentence, but you can imagine that Alice just performs some measurement. It's not necessarily the honest teleportation measurement. It could be just some arbitrary measurement that generates these teleportation keys. So conditioned on her performing the measurement, Bob's EPR pairs are going to collapse in some state. I mean, maybe they aren't affected at all, but maybe they collapse into something else. Whatever they collapse to, you can write that state as x to the E1, z to the D1, x to the ER, z to the DR times psi for some state psi. Right. We don't know what it is. But the point is we know that psi cannot have low energy. So when Bob measures it, it's not going to yield a low energy outcome. So hopefully that makes sense. Right, so, I mean, so that basically concludes the description of this this whole protocol. You know, using the rigidity test, we know that Bob's always going to be honest, and in the energy test, we don't need to trust Alice. Alice can do anything she wants, but basically she can only like we would only be convinced of a yes case if there was indeed a low energy ground state. Right, and so this gives us a classical verification protocol for quantum computations. Let's see, is there anything else I was... Okay, so so that concludes the part about verifying quantum computations. And we're going to move on to another topic, which is, you know, it still uses rigidity in a very deep and fundamental way. Okay, so in this next, you know, in the next couple of lectures, we're going to talk about the complexity of non-local games. Right. So we've learned about a bunch of non-local games. Some examples are like the CHSH game, the magic square game, you know, the repeated magic square game, and so on. And what's really interesting about them is that they have, you know, these rigidity properties. Right. So like not only are these non-local games tests for entanglement, right? Like as a classical verifier, you play with Alice and Bob, and you know they have entanglement, but you can actually certify that they have very specific kinds of entanglement and very specific that they're performing specific quantum operations. So the question that we now want to ask is, well, you know, that's pretty interesting. So we can just think about non-local games abstractly and ask all sorts of questions about them. Like, you know, not only, you know, what other non-local games out there, which ones of them are rigid. We want to ask, like, you know, can you compute the optimal winning probability of non-local games? So here's. Right. So remember that a quantum value just means the optimal quantum success probability. Okay, so like, what do I mean exactly? So I should like formalize this as a particular computational problem, right? So the, you know, the input to this problem is going to be a description of a non-local game. Right, so what does that look like? Well, a game is, you know, just consists of two things, right? It has a question distribution mu and some decision predicate D. So mu is just going to be a distribution over questions X and Y that you can send to Alice and Bob. Right?
Are we assuming two-player games?
Two-player games, yeah. You can think about games with more players, but just to keep things simple, we'll keep it to 2. And this D is just going to tell you when the players win the game. So it's going to be a function of their questions and their answers. Right, so someone's going to come up with some description of the distribution, right? They'll just write it down on a piece of paper, and they'll also describe what this the rules of the game are via this D. And now you know everything you need to know about the game in principle. Right? Like you can carry out the game, you can play it with Alice and Bob. And so the goal is to compute what I call omega star G. So this omega star just means the quantum value. And the star is just for historical reasons is meant to denote like, you know, the players are allowed to use quantum strategies. So this is going to be the maximum over all possible quantum strategies for Alice and Bob of, so you know, you fix a quantum strategy and we'll have a particular success probability in this game. So so you know, recall that like what's a strategy for a game? Well, it's a choice of entangled state that Alice and Bob can use, and also measurements that they'll perform. So the success probability is going to be, well, you're going to sample a pair of questions X and Y. I'm going to run out of space, but once you sample the questions, they're going to generate answers, but you only want to count the answers that are actually winning. So we're going to sum over answers such that D of X, Y, A, B is equal to 1. And the probability that they generated those winning answers is given by this formula. So these are going to be the measurement operators for Alice and Bob. And this psi is going to be the state that they share. Okay. Oh man, this is like really messy, but hopefully you get the point. Okay, so this is like a well-defined computational problem, right? Like there's no quantum computers involved because I can just describe to you this non-local game, writing on a piece of paper, and you just have to tell me what this number is, this omega star G. And the question is there an algorithm to compute this for us? And you know, here I'm not necessarily interested in a fast algorithm. I want to know if there's any algorithm to do this. And so does the statement of the question make sense? Like what we're trying to do? Okay. And there's actually, you know, so this is one version of the question. You can say, well, maybe this number is like, requires infinite precision to actually compute. So maybe that's just asking too much. Can we at least compute an approximation of this number? So we'll talk about an approximate version. So you want to, you know, given a non-local game G, you want to estimate this number to within some epsilon, right? And you can also choose what epsilon you care about. Could this potentially be easier, right? And basically the punchline is that this problem is actually extremely difficult. So here's a punchline. There is no algorithm to solve these problems. Right? Even if you gave these algorithms an unbounded amount of time, they just cannot determine what the right answer is for any for non-local games in general.
I'm struggling to even believe that a little bit. I mean, I could say more, but if you're going to talk more about it, then.
No, please go ahead. So, yeah, what's your intuition for, like, sounds like you think that there should be an algorithm.
Yeah, I mean, it seems like my intuition is kind of the way we've even expressed the problem in the beginning. There has to be some way of like parameterizing all the strategies. So we could kind of, try all of them, sample, from each one, and get, reasonably confident in that value.
Okay, good. So that actually connects really well with what I wanted to say. So you say, well, that's, that's kind of like surprising. Like, yeah, why can't we try some brute force strategy, right?
Isn't the number of strategies infinite? How can you brute force them?
Okay, good question. So yeah, there's a lot to go through here. So right, if whenever you're asked, like, is there an algorithm to solve a problem, it's very useful to say, well, what's the dumbest, simplest algorithm I could come up with to try to solve it? Well, we can like try all possible solutions. And there's one immediate barrier that Yuval brings up, which is we're maximizing over the space of quantum strategies. And this is an infinite space. It's continuous, right? Like the set of all quantum states is a continuous space. So how could a computer algorithm possibly do that? So that seems to pose a problem, but it's kind of a not a very interesting problem, because we say, well, okay, maybe we don't need to do it exactly, but we can like discretize the space in some appropriate way.
Okay, you can make it a discrete, but not finite, right?
Okay, good. So why isn't it finite?
Because if it was finite, then you could solve it in constant time.
Well, I guess
am I not seeing things correct?
It could be finite, but it could be a finite that grows with the size of the game.
Oh, I see. Like, so we get like a series of like games, not a particular game with a particular input size.
Oh, yeah. Okay. So I should have been clear. I mean, for any specific game, there's always some answer, like some number. But what I'm looking for is an algorithm that works for no matter what game you plug in. It will tell you what omega star G is, or some approximation of it.
Okay. Okay, I see.
Yep. So if we discretize the space of strategies, then of course we can only settle for approximate answers. Right?
I mean, couldn't you use rigidity here as well? I mean, maybe you're not guaranteed that you can, but in many cases.
Well, I guess, but we only know of rigidity for just a handful of games, to be honest, like just a select few that we discussed, like CHSH and Magic Square. But you can imagine coming up with crazy games, right? Any type of question distribution and this, D of X, Y, A, B. And you can ask, well, you can ask a bunch of things about the game. Like first, is there any quantum advantage? Like, is there, can you beat the best classical strategy using quantum strategy? Even that is not immediately obvious for any given game. Sometimes it's yes, sometimes it's no. And then in the case that there is a quantum advantage, that, then it's still not clear whether it even has this rigidity property.
Intuitively, it seems like the hardest game to individually find the omega for would be some game where all strategies but one are equivalent, and the one unique strategy is the best.
Mm-hmm.
Where, like, there it would seem that no matter how much you discretize the space, unless one of the points you picked is the best, you won't see your answer in brute force. And there will be no epsilon big enough, except, epsilon equals 1, with which you'll be able to approximate.
Mm-hmm.
But like, if I may,
So there's a little more, I don't think things get that adversarial. So let me draw a picture. So actually what I wrote here was not totally accurate. So the thing that's not a real issue here is the fact that the space is continuous. Like that's not a real issue, because we can just discretize. So you can imagine, here's the space of quantum strategies. And there's some natural notion of distance between two quantum strategies. So let's say you had a strategy S1 here and a strategy S2 here. And just to remind you, what's a strategy? Well, it's a choice of state and choice of measurement operators for Alice and Bob. So if S1 and S2 are epsilon close, however we define closeness, then they can only differ in their winning probability by epsilon. So you imagine, like, if we just carved up the space into a bunch of epsilon balls, so that would discretize the space, right? And we only enumerated over each of these epsilon balls, then we would be guaranteed, imagine that the number of epsilon balls is, let's say it was finite. Then by searching over all of these epsilon balls, we would be guaranteed to come within epsilon of the optimal strategy.
So then strategy space varies smoothly in winning chance.
Yes. I guess that's how we kind of define, that's one way of defining. Oh, well, anyways, yeah, so that's correct. Like if you only perturb the strategies by epsilon according to, let's say, trace distance or something, then that only changes the winning probability by epsilon.
Is there a chance for epsilon discontinuities or something?
Sorry, ask that again.
Is there a chance here for discontinuities in the epsilon landscape?
No, so it's a continuous like this space is continuous.
Okay.
Yeah.
Well, continuous spaces can still have discontinuities in functions defined on them. Like tan over the real number line.
Right. Okay, good. So so I guess it's whatever the right thing is. Like the point is that the winning probability is a smooth function of the strategy space. There's like, yeah. So if you, it's just what I said. I mean, and it's sort of like, maybe not hard to see. You just look at the formula, like how is winning probability defined? Well, it's just this like linear combinations of these expectation values. So if you perturb this state just by a little bit, then this whole value can't change by too much. And similarly, if you change the operators by just a little bit, you're not changing much, right? So it should be intuitively clear that this winning probability is a smooth function of strategy space. Okay, so that's one thing. But there's another way in which the space of strategies is infinite, and it's not coming from the continuous nature of quantum strategies. Any ideas about how else it could be infinite?
Your strategies could have an arbitrary number of qubits per player, like a finite number of qubits per player, but arbitrarily large finite number of qubits.
Exactly. So when we're saying quantum strategy here, I haven't said how many qubits are involved, right? The players get to pick how many qubits they want. So like the CHSH game, it requires 2 qubit strategies to play optimally, right? You just need 1 EPR pair. For the magic square game, you need 4 and no more than 4. But in general, people could come up with crazy games where maybe you need 100 or 1,000 or 1,000,000 qubits to win, right? So if you were to start trying to do a brute force approach, you would say, well, I'm going to start searching over the space of strategies with 2 qubits and see how well I do. And then you can certainly enumerate over all possible strategies there, and you will find like an epsilon approximate best 2 qubit strategy. But then you move on to 3 qubits and 4 qubits and so on, and you wouldn't know where to stop.
So like in the no case of the decision variant of this problem.
What's the no case?
Like if you replace your question by giving the given the description of the game and k, is the quantum value of the game at least k?
Mm-hmm.
And then like the yes case is fine, but the no case you could run forever.
Right. Right. So the key point that is important to know here is that if we fix the number of qubits to say n, then it is possible to brute force over a discretization of all n qubit strategies to find the epsilon approximate best n-qubit strategy. So you can certainly do that, but we just don't know. Like if someone hands you a game G, like, and says, well, there's some optimal strategy out there. How many qubits does it require? It's not clear like how to figure that out.
When you said there's no algorithm to solve this problem, did you mean there's no known algorithm, or it's known that there's no algorithm?
We know there is no algorithm. So don't go try looking for one.
And if you do fix n, can you do something better than brute force? Or is it
great question.
not known?
So let's try to do an estimate. So if you have n qubits, I think the I think the best is brute force. So how long does it take to brute force over n qubit strategies? Well, the dimension of the space is 2 to the n, right? And the number of states, like if you discretize, the number of states in dimension 2 to the n is 1 over epsilon 2 to the n, roughly speaking. And so you need to take that much time in order to search over all those epsilon balls. And I think that's, as far as we believe, essentially the best you can do.
Like, is it known to be complete for some complexity class, or is it just like a belief?
I think it's based on some complexity assumption.
Okay, sure.
It's still like it seems to me that arbitrarily allowing more qubits at some point is going to stop giving an advantage, and I could see that it being difficult to prove that you've reached that advantage. But this theorem seems to be that we've proven that it's impossible to prove that you've reached that advantage. And that seems to me very surprising.
Yes, exactly. So we're going to see how this could come about. So this basically, this is what we're going to like see, like have it unfold over like, today and in the next lecture. So I want to dwell on this n qubit thing just for a little longer because it'll come up again. So let's define alpha n to be the, let's say to be epsilon approximation to best n qubit strategy. Winning probability, right? And I just claimed that alpha n is computable, right? So if I told you what n is, you can definitely compute it. I mean, it'll take you like an ungodly amount of time, but at least there's some algorithm to do it. And the other thing about these alpha n's is that they form like a what's it called, a non-decreasing sequence. So if you have 1 qubit, you can't do better than 2 qubits, and that's, you can't do better than 3 qubits, and so on. So this is going to form a non-decreasing sequence. And if you're to sort of chart this out, right, so let's let n go this way. So for a given game G, there is some optimal winning probability, right, that we're trying to establish. And if you plot these sequence of alphas, you're going to get some sequence that this. And actually what we know is that these alphas will converge to the omega star G. We just don't know when it will converge, right? And so let's say you're computing these alpha n's, increasing n's, but you just don't know like am I close or am I far? Or, right? And so, so that's kind of the problem.
Is this omega star G like a supremum over all winning probabilities, or is there always a optimal strategy?
Okay, great question. It actually is a supremum. So that's kind of like a subtle but actually very important technical detail. So it's not always achieved, but which actually is very interesting. But for now, yeah, we can just think of it as a max. But sometimes, yeah, you can actually never achieve the omega star. Right. Okay, so where were we? Okay, so you know, I claim that, you know, the punchline is there is no algorithm. So somehow we have to prove that there is no way of telling how close we get to the optimal value, right? And that's kind of like a weird meta statement. Like, how do you know we can never know something, right? And this question about the complexity of non-local games is actually tied to a bunch of different questions that people have considered in different areas in like kind of a surprising way. So, you know, what are the connections? So one is, well, clearly complexity theory, because we're talking about what is the complexity of a computational problem. And in fact, it's related to this complexity of a class called MIP star, which is quantum multiprover interactive proofs, right? So that's one connection. Another connection is to mathematical physics. And there, the question that people asked is there a difference between finite versus infinite dimensional entanglement? Difference in a useful sense. Like, is there something that you can do with infinite dimensional entanglement that you cannot do with finite dimensional entanglement? And there's a third connection, which doesn't even involve any physics at all, but talks about functional analysis. And there was this question that was open for quite a long time, known as the Connes Embedding Problem. Right, and you know, if you look at the statement of this Connes Embedding Problem, it's like extremely esoteric, and especially if you're not from pure math, and it talks about these von Neumann algebras and things like that, and there's ostensibly no connection to physics or much less complexity theory. But it turns out that settling this question about whether there's an algorithm to compute the value of non-local games gives a resolution to this open math problem, or that was open. Okay, so it's kind of crazy. Like, how can all of these three things be related? And so, basically, that's kind of what I wanted to talk about for the rest of today. And once we see how all of them are connected, and then I think when we pick up next time, which is in 2 weeks, we'll start to see at least the ideas and how you can actually prove the non-existence of an algorithm. Okay, so let's take a 5-minute break, or let's come back at 5:15, and then we'll pick it up there.
Just a small question. Oh, sorry.
Why don't we have a class next week?
Oh, because next week is reading week, I think.
Okay.
Yeah, so it's just a break.
Just a question. Is the protocol you presented today with the quantum teleportation like a improvement over JFNG's protocol and Nataraja and Bidix protocol on QMA completeness? Because this seems very similar and I just mentally couldn't connect them together yet.
Oh yeah, it's a follow-up, and it's like a very big simplification of those. Like conceptually, it's much simpler, right? Like all you do is just this teleportation, and so it's like this protocol.
Okay.
It's just like takes like a couple pages to analyze, whereas the previous stuff was like much more involved. But it really falls all in that vein.
Because I was actually reading those work like yesterday.
Oh yeah.
This just makes a lot more sense to me. Anyways.
Yeah. No, this protocol, it's by Alex Grillo, and it's just very clean, right? Like it takes like a lecture to explain.
Unrelated, were those your cats or single cat going crazy in the background?
It's just a single cat, yeah. Yeah, that's Roosevelt. It's a quarantine cat. Like we got Roosevelt in June. So he's been providing endless entertainment for us.
I'm surprised we got this far in with no cat sounds.
Huh. There's definitely been cases that during lecture when he's gone crazy, but maybe
He was on the problem set.
he was. Oh yeah, exactly. Right. You saw how to generate an approximate version of this cat.
And during one of the office hours, he took your place.
Oh yeah. Yeah. So he's made cameo appearances.
Yeah.
I mean, yeah. I think especially around this time he starts getting very antsy because it's close to dinner time.
And he doesn't know about daylight saving, so he probably thinks it is dinner time.
Oh yeah, that's right. Yeah, so we're trying to. I mean, I sympathize. I also don't understand daylight savings time. I'm kind of afraid to check whether there's any news that's blown up in the last hour. But I imagine there would be looks on your faces if something happened. So hopefully not.
Do you mind just putting up the end of lecture 8 notes on the screen? I just want to look at it for a little bit. Thanks.
This one?
Yeah.
Okay. Yeah.
To the best of my knowledge, it looks like nothing has happened. So
That's great. All right, so shall we go back? All right, so let's start seeing what are these connections. So let's start with the first one, which is this complexity question, like the complexity of MIP star. So if you remember from one of our earlier lectures, we talked about different notions of proofs, right? We talked about NP proofs, right? These are deterministic, classically verifiable proofs. QMA is these quantum proofs, right? It's like there are also these interactive proofs, right? And that's what this MIP star falls into. We also talked about these PCPs, these probabilistically checkable proofs. Every time someone came up with a new notion of proof that has a corresponding complexity question, right? You can say, what sorts of statements can you verify with that particular proof system? Right, so in particular, we saw that this, if you have a verifier, polynomial time verifier interacting with an all-powerful prover, the types of statements that you can prove are ones that are exactly the ones that you can solve in polynomial space, right? So this is a verifier interacting with a single prover. What if you have interactions with multiple provers, right? So here you have a verifier interacting with two or more separate provers. Then you get this class MIP, stands for multiple prover interactive proofs. And it's equal to an even bigger class, presumably, called NX, or non-deterministic exponential time. And so those are kind of like the, what we know in the classical setting. And then in 2004, computer scientists who started getting into all this quantum stuff said, well, why don't we make a quantum twist on interactive proofs, right? So here the verifier and provers are all classical, but what about quantum interactive proofs? Like, what changes there, right? So let's say we have a quantum verifier. One way of doing it is you can have a quantum verifier, right? So I'll just call that QV, and it's interacting with a quantum prover, and they send messages back and forth, and at the very end, the quantum verifier has to decide whether to accept or reject. So this, the types of problems that you can solve in this model yields a complexity class called QIP. Okay, quantum interactive proofs. What is the complexity? Well, it turns out to be no different than if you had classical verifiers. So it's the same as IP. Okay, so QIP equals p-space was a result that was proved not too long ago, about 10 years ago. So that's one model. But the other model is this MIP star. So here we have two provers. They're quantum provers, but they're interacting with a classical verifier. Okay, and so the verifier only sends classical messages. Now, what's quantum about it? Well, the provers are allowed to share entanglement. Right, so this should start looking very familiar. This should look like a non-local game. So they came up with this model of interactive proofs. They said, well, here's another one. What is the complexity of MIP star? Right, the star refers to entanglement between the provers. And this question was asked in 2004, and they realized, the people who raised this question realized that this was a very mysterious question. Like, you can define this class and you can say, well, how does it compare to the situation where the provers don't share entanglement, right? The MIP setting. And they realize that it's actually not obvious what's the relationship between the two.
Is in MIP are the provers quantum?
We think of them as being unbounded in power, so they can be quantum computers for all we care, but it doesn't really matter since they're allowed unlimited computation power. What they're not allowed is to use entanglement to coordinate their responses. Right, so we can try to think about in one way. So, so in an interactive proof, we think of in the no case, the provers are trying to convince us of a yes answer, right? So they're trying to fool us. Right, so since the provers now have this additional resource in the quantum setting, like they have this entanglement, we might think, well, maybe that gives them extra power to fool us, right? So that would mean that this class MIP star is actually less powerful than MIP. Right, so this is one, maybe one intuition for why you might expect, okay, actually giving provers this extra power is detrimental to your interactive proof, right? But on the other hand, there's another intuition that suggests it could be that MIP star is more powerful, right? If the verifier now knows that the provers can share entanglement, the verifier can check additional things, right? It can, for example, check for the existence of entanglement by playing the CHSH game, right? This is something that non-entangled provers could not have done. Right, and here we don't mean more in a computational sense, because we're assuming that these provers can compute anything they want. It's we're just asking them to, by more I mean more in the sense of what correlations they can exhibit. Right, so there's two different directions that conflicting pieces of intuition that say that really make it not clear like who has the upper hand in this kind of proof system. Does the verifier have more power now that it can ask the provers to do quantum things, or can the provers use this entanglement to always fool the verifier? So for a long time, the complexity status of this MIP star was very unclear. For the longest time, the best the only bound that we had was kind of a trivial one, was that IP is contained in MIP star. Basically, that's saying the verifier can always just ignore Bob and only talk to Alice and just run a typical traditional interactive proof with just one prover. So of course, you can always just do that. So that's why anything that you can be convinced in the IP setting, you can also be convinced of in the MIP star setting. But what about the other side? And it wasn't even clear if there was any computable upper bound on this. And so just in terms of like complexity theory jargon, there's a class called RE that it's sort of like the trivial thing that includes MIP star. And what is RE? It stands for the set of recursively enumerable languages. And this complexity class is so gigantic, it even includes things that cannot be solved on by any algorithm, right? So in terms of like the complexity landscape, here's NP, here's P, here's P space, right? In terms of harder and harder problems, here's NX, for example. And then if I wanted to draw RE, I'd have to draw something that just like really like, I mean, of course, things are not to scale, but to give you a sense that it includes uncomputable problem.
Does that mean that there's no meaningful definition of something being RE complete?
Oh, great question. There is a notion of an RE complete problem, and that's the halting problem. So actually, let me just get into that. Okay, so I'm going to do a quick refresher of the halting problem in case you're not from a computer science background. So the halting problem is, suppose I give you a description of an algorithm, and I ask you to run the algorithm. I want to know, does this algorithm ever terminate, right, in any amount of time? So sometimes you run an algorithm and it gets stuck in an infinite loop and you just have to kill the program, right? Other times the program runs for a short while and it stops. Other times a program will run for a long time and it will eventually stop. The halting problem is to say, can you just tell me if it ever stops? And one of the first things that was proved in computer science is that the halting problem is not solvable. So this is due to Alan Turing back in the 1930s. Right? There's no algorithm to figure out if other algorithms in general ever terminate. And the way you prove this is kind of through a self-referential argument, right? Like you say, well, suppose there was such an algorithm that was very clever and could figure out when algorithms would terminate. Then you can basically ask it to figure out if it terminates on itself. And you kind of like do the opposite thing. Like it says, well, do I ever terminate? If I think I terminate, then I'll actually not terminate, in which case it will have output the wrong answer. Or if it says I don't terminate, then I will stop, right? So it's kind of like this self-referential, self-defeating logic argument, right? And the set RE is the set of all problems that can be solved if you could solve the halting problem. All right, so RE is like an enormously huge class, clearly. And you know, basically the only thing that we knew is that if you can solve the halting problem, then you can, you know, then you can solve any problem that's decidable by an MIP star. Which, you know, this is not a situation that we're used to in complexity theory. Like in complexity theory, we can say, well, even if we're being really dumb, we can always come up with some algorithm that runs in, you know, exponential or doubly exponential time that will eventually solve the problem. But here, that's not even the case.
So this is interesting because these uncomputable problems are well-formed questions, right? They're not of the same shape as like, do colorless ideas float easily? They're meaningful and cannot be answered, which to me might suggest some like really esoteric physics connection between problems that you can solve if you can solve the halting problem and things that are possible if you can violate, say, the uncertainty principle or the speed of light in vacuum.
Aha. Yeah, that's, well, you hit on a bunch of really interesting points. So the first one, yeah, I definitely want to emphasize. So in this halting problem, like for every algorithm, there's a well-defined answer of whether it halts or not eventually. I mean, it either halts or it doesn't. And the question is, can you determine that answer? Turing says you cannot in general. And then the second point you raise is connection of uncomputable problems with physics. So I guess it you know, connects back to this thing we were talking about, I guess, a bunch of weeks ago about this Church-Turing thesis, which says that any physical process, well, okay, so the original Church-Turing thesis says that any physical process that's out there, you can simulate with an algorithm. I mean, this simulation doesn't have to necessarily be a fast simulation, but you know, you can simulate it. So, okay, and then you're saying, well, suppose that, you know, we had different laws of physics. For example, maybe things can travel faster than the speed of light. Can you then solve uncomputable problems? I think even in many cases, even if you change the laws of physics in pretty wild ways, the resulting models of computation that can come out still don't allow you to solve the halting problem. So, you know, just to, like, for example, some people say, well, so what if these things called closed time-like curves exist? Basically, it means like time travel is possible. And technically speaking, like general relativity does allow for closed time-like curves to be possible. And you think, well, if that's possible, why can't you just travel back in time and, like, you know, solve unsolvable problems? But people have actually shown that under very natural models of time travel, you can still only solve problems in p-space and in polynomial time. You can't solve uncomputable problems. Yeah, so
have a link to such work.
Yeah, you can look up. You know, this is kind of like a hobby project of people, and they don't like to publicly admit that they work on time travel and complexity theory. But like, for example, Scott Aronson has a paper on stuff like that.
Time travel.
Well, the technical term is closed time-like curves,
Okay.
so it doesn't raise red flags. But you can look that up, and you know, they show in this model you can solve like problems in p-space and so on.
Right, and I think it's also worth mentioning that there's natural examples of undecidable problems that come from physics, like this recent undecidability of the spectral gap result.
Mm-hmm. Right. Yeah. So you know, if you come from, that's a good point. Like if you come from more of a physics background, this halting problem seems kind of like why would you care about it? So here's a physically motivated problem that is undecidable. imagine that someone gives you a translationally invariant Hamiltonian that's on an infinite number of qubits. So, let's say you have, an infinite number of qubits on a lattice. So it's like a continuum. And between every neighboring pair of qubits, you just have a Hamiltonian term. And so, this gives rise to a local Hamiltonian on, well, an infinite number of qubits. And the question is there a gap between the first eigenvalue and the second eigenvalue of this Hamiltonian? And it turns out that there is no algorithm to determine this. There is a well-defined answer, but you cannot solve this problem in general. So there are examples of this. Okay, so where were we? Talked about halting problem. Yeah. So, anyways, so this question of what is the complexity of MIP star? It's very mysterious, and the point is that since MIP star looks very similar to like a non-local game, it shouldn't be surprising that the complexity of MIP star is intimately connected to the complexity of non-local games. In the sense that, like, if there was an algorithm to compute the optimal winning probability of non-local games, then you would actually have some reasonable upper bound on the complexity of MIP star, and vice versa. Okay. So that's the connection. Okay, so what about number 2, mathematical physics? Right, and the way I'm going to phrase the connection is, here's the question. Can infinite entanglement help Alice and Bob in a non-local game? Right. So I haven't been that formal with how I've described like what quantum strategies are. Like I said that a quantum strategy consists of a quantum state and measurement operators by Alice and Bob. But I've kind of implicitly assumed that a state is defined on a finite number of qubits, right? Like you can choose as many as you want, but it has to be a finite number. But you say, well, what if Alice and Bob share an infinite number of qubits, right? Maybe you can consider strategies of that nature, right? And this is well defined. People do think about those things. Yeah.
So this would be an infinite number of qubits and not specifically like a continuous entangled state. Like what if instead of sharing, a qubit system, they shared some system whose Hamiltonian is has an infinite eigenspectrum, like a weird or any molecule.
Right. Yeah, that's also another model. So actually that's a good question. Like there's different ways you can actually formalize what infinite entanglement can mean. So here are different models of actually, let's say different models of quantum strategies. Right. So one model is finite dimensional tensor product model. Right. So here, we imagine that the shared state that they have is going to be on a tensor product of two spaces, CD, tensor CD. You get to pick your favorite D, but it's still finite. And then their measurement operators are just projections on CD. Right? So, this is the thing that we've kind of implicitly assumed what a strategy is. Well, you can say, well, let's not restrict ourselves to finite dimensional ones, but let's say infinite dimensional, but still tensor product spaces. So now the state psi is going to belong to a tensor product of two arbitrary Hilbert spaces. The Hilbert spaces can be infinite dimensional, right? So in particular, they can capture the Hilbert space of a molecule. Right? And similarly, the projections also act on this space. Right? So that's one model. And you can also consider their optimal winning probability in this case too. There's a third model, which is the most general, which is called the commuting operator model. Okay, and here, this is kind of the weirdest one. So we have a state that Alice and Bob can share, but it lives only on a single Hilbert space H. Okay, so there's no notion of like tensor product between Alice and Bob. Their measurement operators also act on H. But we're going to have the constraint that Alice and Bob's measurement operators always commute. And what is that supposed to capture? It's supposed to capture the fact that Alice and Bob cannot signal to each other. So if their measurements always commute, that means they can, it doesn't matter what order in which they measure. So intuitively, it means they can never send a signal to each other by making a measurement. All right, so you can say, well, can we also consider strategies in this commuting operator model? And this last one might seem kind of weird because we say, well, normally Alice and Bob are, we have to separate them, right? So Alice is in one side of the galaxy, Bob is in the other side of the galaxy, and they clearly live on, different Hilbert spaces. But actually, in the most general model of quantum physics, which is quantum field theory, oftentimes the way things are described, as far as I understand, there isn't always a natural tensor product decomposition between two spaces. Okay, so I certainly don't know anything about quantum field theory, but this is what all my quantum physicist friends tell me. In the theory, like you can have these two regions of space-time where like these two regions cannot causally affect each other. And then if you just mathematically model what's going on with them, you just cannot separate them out into, Hilbert space 1, tensor product Hilbert space 2. And so this is where this commuting operator model comes from. Okay, so given this, we can say, okay, there's now more fine-grained distinctions between these different models, and we can go back to non-local games and say, does it make a difference if we choose strategies from any one of these models? Right, so we can, given a game G, we can define, so omega star, what we really meant by this was optimal winning probabilities, or supremum of winning probabilities over finite dimensional tensor product strategies. Okay, we can define, let's say omega, let's call it omega inf, for lack of a better term, infinite dimensional tensor product strategies. And then we have omega commuting operator. So this is where you say you can pick any commuting operator strategy. So what's the relationship between all these different winning probabilities? And it turns out that one relationship is easy to see, that we have these inequalities. And this sort of follows by definition, right? Like if you're allowed an infinite number of qubits, then clearly you can't do worse. So that's why you have this inequality here. And the commuting operator model is the most general because this Hilbert space H could have actually just been a tensor product of Hilbert spaces. So, these inequalities follow by definition. And in fact, the first two are equal. And this actually follows from the fact that that omega star is defined as a supremum. And basically what it's saying is that if you had an infinite dimensional but tensor product strategy, you can approximate it arbitrarily well using a larger and larger finite number of qubits. Okay, so really we shouldn't distinguish between finite dimensional and infinite dimensional in the tensor product case. So really the interesting question is, what is the relationship between omega star and omega commuting operator, right? Like if they were equal, then it would say that these very, very general quantum field theory commuting operator strategies, you can always just approximate them as good as you want using finite dimensional strategies. And that would be like, really nice because we would just say, oh, let's just focus on finite dimensions. And this is like the mathematical physics question, like, can commuting operator strategies be approximated arbitrarily well in finite dimensions? And this question is known as Cyrilson's problem. Right, so remember, Cyrilson is the guy who proved that the CHSH has this 85% maximum winning probability. Well, he also raised this question. And the first thing to say here is that this really is a question about finite versus infinite dimensional entanglement. So I should really say inf TP, because otherwise it might be misleading. And why is this the case? Like, that's because if you took a commuting operator strategy and you guaranteed to me that it was finite dimensions, like the Hilbert space it was defined on is finite dimensional, then in fact, you can always find a tensor product decomposition within it. Right, so these are one and the same. So really the only, like the question is, like they can only be different if we're talking about infinite dimensional commuting operator strategies. So, you know, in some sense, this question is kind of, you know, it's pretty simple. It says, is there a game out there for which, you know, like suppose that they were different. Suppose there existed a game where this tensor product value was like strictly less than the commuting operator value. It would mean that if Alice and Bob had this really, you know, crazy infinite dimensional strategy that they used in commuting operators, that they could achieve a winning probability that no matter how many you know, finite number of qubits that they use, they couldn't even approximate, you know, just using a finite dimensional strategy. Right, and that there really is like a qualitative gap between infinite and finite dimensional entanglement. So that'd be kind of interesting because then, you know, a lot of people debate whether is the, you know, I mentioned that quantum field theory is really like maybe our most accurate theory of nature. And at its core, quantum field theory like has all these infinite dimensional Hilbert spaces floating around. So you can say, well, is that actually an accurate description of nature? Because the other view is that actually fundamentally nature is discrete. Like if you zoom down small enough, there's this thing called the Planck scale where, you know, it's sort of like the minimum unit of space and time. So maybe actually everything is discrete and therefore everything's, you know, finite dimensional. And if there existed a game, then in principle, there could be an experimental test to distinguish between the two settings, right? Just like, you know, the whole point of this Bell test of a Bell inequality is to determine is nature classical or is it non-classical, right? And then you can just play the CHSH game and you can tell that it cannot be described by a classical theory. Similarly, if you had such a game that had a difference between commuting operator and finite dimensions, you could distinguish between whether nature was, you know, fits better in the commuting operator model or it can be described using finite dimensions, right? Because if you played this game and you saw winning probability that was, you know, closer to this omega co value, this would give you evidence that, you know, nature goes one way than the other.
So suppose we found such a game. Do we actually have, like, do we actually know of a way you could implement a strategy like that?
Excellent question. So if I said that there exists a game, then that's not enough to actually carry it out an experiment. You're right. You'd furthermore have to actually come up with some physical theory that says, here's some physical apparatus that you could set up that would actually achieve the commuting operator value of the game. And that's far from given, right? In fact, so what, I phrased it in this way, but practically speaking, that this is not really possible given our understanding of physics, because anything that we can, run like in a lab in like a bounded amount, like on Earth, you can actually we can describe basically using finite dimensions, right? Because there's only like a finite number of qubits that are in your lab. As far as we can tell, I don't know, maybe the physicists in the audience like have a different take, but I don't know if we have any genuinely infinite dimensional physical phenomenon that we can run an experiment with. I mean, I know Sumner mentioned that molecules, like the Hamiltonian, is infinite dimensional, but I'm not sure if, we actually see like infinite dimensional behavior in some sense.
We don't really. A general principle in a chemical systems Hamiltonian is that even just for the bound states, which are infinite, as you go into the higher and higher excited states, they get more and more degenerate and less separated. And accordingly, the ground state dominates at anything but infinite temperature. You'll much quicker get to thermal decomposition of the entire system than you'd get to some situation in which you've thermally mixed the system such that it's distributed about equal over all of its states. Like even tungsten will plasmize at something like, I think, 10,000 Kelvin.
I see. So if I understand you correctly, you're basically saying like the Hamiltonian technically allows for like any range of energies, but at a certain energy range, your like lab equipment or your material is going to like melt or explode, and then you don't have a valid physical description of the system anymore. Is that kind of what you're saying?
More or less. There's no way to. The other way you would do it would be like, say you were to take a single electron in a molecule and excite it. The control process you would need to get above a pretty low number of excitations would be like the simultaneous interaction of hundreds of coupled photons. And it's just not really a process that seems viable. And furthermore, like you're saying, okay, we can't get a coherent movement into one excitation, but what if we, were to try and get it to thermally mix enough that we're sampling from a mixture of basis states? By the time you're getting into the upper states, you've blown the molecule up. So even at room temperature, even at above room temperature, at any temperature where your Hamiltonian is a valid description of the behavior of the system, the ground state, maybe some low-lying excited states, if the gap is very small, are sort of all you've got.
Mm-hmm. Yeah, I guess one thing that's I particularly don't have very good intuition for is that for these types of arguments, it's hard to separate out like what are the objections that come from practical concerns, like, oh, your lab's going to blow up, versus there are like fundamental, like basic fundamental, like theoretical reasons why something couldn't be done or the other. And at least sometimes it's not clear to me what the dividing line between that is. So with this like Bell test for infinite dimensional versus finite dimensional like physics, this is certainly something that's very, very in principle. Like there's no prescription for how actually we could run such a Bell test, even if we knew a game existed. So it's mostly of interest to mathematical physicists who want to like come up with like a well-defined mathematical formulation of quantum field theory and so on. But at least philosophically, it's kind of interesting that one can think of it in this way. Okay, so it's 6 o'clock. I think we'll pick up in a couple weeks. So next week there's no class. We're going to take a break, but we'll pick up in 2 weeks and sort of continue the story and see how it all comes together, and then we'll start to see actually the details of how you prove the non-existence of an algorithm for non-local games. So thanks a lot.
Thank you.
Thanks.